So our first speaker today is a pretty interesting guy. About 2 months ago, I started sending random emails to random academics in the space of streaming and sketching. And one of the emails I sent was to Muthu, and I had no expectation that he would respond. There's no reason he would reply to my email, but he did. And he was like, "Yeah, I've seen your blog, and I think the stuff that you're doing is pretty cool, and I'd love to hang out and talk shit." So we did, and then he realized that we're in advertising, and advertising is also one of his sort of current passions, I guess. So we talked even more. And then again, over the last few weeks, I've gotten to know him reasonably well. And the first thing that you realize when you meet Muthu is that he's brilliant. He's one of the smartest people I've ever met, and you can tell immediately how quickly he understands concepts. And the second thing that you realize directly thereafter is that he's crazy. He's a really, really crazy guy in a really, really good way. And he's been a lot of fun to hang out with in the last a few weeks and sort of get to know him. And I'm super excited for his talk. When you first start looking into sort of streaming and sketching algorithms, you kind of get to Bloom filters maybe as the first thing. And then pretty much the second thing is probably count min. And count min is so elegant in its simplicity. It takes 1 second to explain to somebody, and it's so broad in its application that it's amazing. And it's a great honor to have Muthu here to talk to us and give us a little bit of the history of this sketch. So welcome. How did we do this?
There's a key there.
Full screen?
Yeah, that's good. Perfect, thank you. Yeah. Matt, thank you for having me here. It's been a few years since I thought about these problems, and I remember this joke about this man who says that 10 years ago I thought that I was surprised by how stupid my dad was. Okay? And the other day I was thinking about it, and I realized how much my old man had learned in the last 10 years. Okay? And I feel like that here, sort of rediscovery of this field. I also have to tell you that when I was a graduate student, I worked on an area called string matching. And then, as I was graduating, I ran into somebody who gave me a problem on an area called load balancing. And I worked on a bunch of those problems. And then a year later, I got an email from a headhunter who said, I'm looking for people who have expertise in string matching and load balancing. I thought this was crazy. Something similar when I met with Matt. I always thought about streaming algorithms. I thought about advertising. I never thought I would meet someone who would say, I like streaming algorithms and I do advertising. Seemed like a setup. Okay. But then, since then, I discovered lots of wonderful things about AK, and I'm very excited to be here. I want to start with a simple puzzle. Okay, I don't want you guys to spend a lot of time solving the puzzle, but there's a story here. Okay? The puzzle is that it's a two-player game, N and M, nagger and mover, and there's a bunch of seats arranged in a circle, numbered 1 through N, and both players get to see all the seats. And you have the player N sitting at chair number 1, and the other player is not seated in the chair. Okay? And they take turns playing the game, and each the moves are as follows. Okay. N calls out how many places he would like to move, how many chair locations that he would like to move. Okay? So he says, I like to move 5 places, 3 places, whatever. And M determines which direction N can move. Either move clockwise or counterclockwise. Okay? So the game goes and repeats in this manner. Every step, N says, I want to move 3 seats or 5 seats, whatever he prefers to move, and M determines which way he moves. Okay? And what N is trying to do is make sure that he sits in as many seats as possible. Ideally, he wants to sit in every one of the N seats. Okay? It doesn't matter if he visits the same seat many times. He's just trying to get to as many seats as possible. Okay? And what M is trying to do is to make sure that N sits in as few seats as possible. Okay? And it's a very simple game in the sense that There's no informational constraint. They know all the seats. They know n. There are no computational constraints. You assume that each person can solve complicated problems, be infinitely smart. You're just trying to determine this number, a function that says given n, what is the maximum number of places that n can sit in? And assuming that it's infinitely smart, and what's the least number of positions that n can restrict n to? Okay? So if you define this function fn as the largest number of seats that n can sit in, you want to study this function. And at the very least, you want to make sure that f of n is not equal to n, right? Because then it's not may not be a very interesting problem. So you can start out with thinking about what happens if there are only 2 seats, 1 and 2. Right? If n starts at position 1 and says, I want to move one place, then no matter whether clockwise or counterclockwise the person moves, they get to the second position. So if there are only 2 seats, f of 2 is 2, no matter how smart m is, they cannot stop the player from going to the other location. Okay? So f of 2 is 2. The problem gets interesting as soon as you look at n equals to 3. Okay? If there are 3 seats, 1, 2, and 3, and n starts from 1, then if he wants to move 1 position, m will move them clockwise. If he wants to move 2 positions, he'll move them counterclockwise. Which means that he'll go from 1 to 2, no matter what his call is. And likewise, you can move him from 2 to 1, no matter what his call is. So in other words, you can make sure that if there are 3 seats, 1, 2, and 3, and the player starts at 1, then you can make sure that he never visits the chair number 3. Okay? Just by moving them between 1 and 2. Okay? You can look at other variations. It doesn't matter whether he calls 1, 5, 7, and any multiple of these things, any large number. It's only modulo 3 that matters. You can make sure that the player basically shifts between 1 and 2 and never visits 3. So f of 3 is not equal to 3. F of 3 is 2. And that means the problem is interesting. Right? Now it's beginning to be interesting. It's not the case that n can sit in all the places. And it turns out that f of 4 is 4. Okay? So if you go back to 4 seats, then you can actually n can sit in all the 4 seats. Okay? No matter how smart n is. Okay? Then you start thinking about this function and trying to figure out what's going on here. Okay? Okay? And it turns out that this is actually a very nice function. Okay? I will let you guys figure out what the function is. Okay? And it's not a very obvious, very simple function. I mean, it turns out after thinking about it, you can write actually a formula, and then you can generate the whole sequence of n. And it turns out that the sequence was not in the encyclopedia of sequences, so we managed to get it added to the encyclopedia. But it's a nice puzzle to think about. And the reason I mentioned this is that it's good to wake up in the morning thinking about a puzzle. Also the fact that this was the second time I tried to name a game after the authors of the paper. Okay. And, and I didn't quite succeed with this game. No one has heard of this game. So I thought I'll start with a failure. So let me talk about the things you guys are more focused on, big data. Okay. I want to just sort of use 3 examples to motivate the kind of questions we think about. So on the left column, leftmost, is the first project I did with a very large amount of data. Okay. I had a contract with a very large cell phone company, which gave me all the CDRs, or call detail records, of every call that was made. And I had to write reports about the market. Okay. The reports were not very simple reports like how many calls did a person make, but they were more like what trunk groups are being used in Chicago often. And so very network level specific things. I had to know what an Ericsson switch does, what a Nortel switch does, what a Lucent switch does, and how they handle calls in different ways, and what happens in a mobile-to-mobile call. Like what happens when I pick up my cell phone and call Matt is a series of intermediate calls, and I had to figure out all this stuff. And I had to write very detailed technical reports and solve problems that would be hard for them to solve using the network alone. And data analysis was the right way to go. Okay? So about terabytes of data, we used to write reports. But what is important is that this is a kind of analysis done by a small team of analysts like us, like half a dozen people doing it. And we used regular file systems, regular scripts to run it on multiple machines, and we didn't really use any special purpose hardware or special purpose storage systems for this. Okay? And we never wrote a paper about this, even though we solved lots of interesting problems. Okay? Because it was a contract, and we just did detailed studies. Okay? Now, is that a big data problem? No, I would say that we dealt with a large amount of data. We did lots of interesting things. But a lot of people in the audience wouldn't think of it as a big data problem. The second category, or the middle column, is all the data is dealing with not telephone records, but IP networks. Okay? So in IP networks, there are, as all of us know, there are packets, and there are many, many connections for each one of the requests, and there are tens and hundreds of packets sent for each of the connections. And so there's a lot more data. Okay? It's terabytes per hour or per minute, depending on the kind of backbone bandwidth you're looking at. And you don't think about reports in months time scale. You think about more like days, minutes, and hours. Okay? If there's an attack on the network, you want to detect it as soon as possible in minutes. Okay? And again, the analysis is done by a small number of analysts, in some cases researchers, because many of the systems don't exist. Okay? But you need very specialized hardware to do this kind of analysis, okay? Because the packets are going through the routers at a very high speed. So you need some sort of an optical splitter that takes the traffic, copies it over to a fast buffers, write them as fast as you can, and read them as fast as you can, because the data goes very fast. Okay? And this needed research-level development of new tools, and this is where I got started thinking about streaming. Okay? And this is an area where a few big companies needed this kind of analysis, and there was a lot of research done, and you needed very specialized hardware for doing this. Okay? And the third category is the amount of data that probably most of you are more familiar with, right? It's a big data at the application layer, at the layer 7, where you collect logs of search queries, you collect logs of advertising, you collect all the connections at a high level. And now this is a very large amount of data, mainly because of how the internet has grown. And sometimes you need analysis in seconds. In spam and other control, you need analysis in seconds, and sometimes you're happy to do it in months at a time, quarter at a time, marketing reports, and so on. Okay? But one of the nice things is that this becomes such important business that the analysis is done not by a small number of analysts, but by a large number of engineers. Many of these companies have people who can write code, 80 engineers, hundreds of engineers analyze this. Even some of the marketing agencies have a large amount of IT people analyzing this data. Okay? It's a very different world from the first two worlds where this data was with a small number of people. Right? And a typical way these guys do it is using a large number of machines, and there's a bunch of systems work on this. Right? So I use these kind of three examples to at least tell myself in what area I work in. Okay? There's a large amount of very useful stuff you can do with existing file systems and tools, and that's the kind of thing the cell phone records could do. And a large number of new research happened with streaming analysis and the sketches that can't happen because we looked at IP traffic data. And a large number of systems got built because people looked at very large big data in the internet scale. Okay? So these are the three regimes of data that I think of that are interesting from big data. Okay. And dealing with packet data generated the whole idea of streaming algorithms that I'll talk a little bit more about. And dealing with hundreds of machines or hundreds of thousands of machines gave us to MapReduce algorithms. I'm being sort of vague about this because there's Hadoop, there are variations, but roughly multiple machine algorithms. Okay? But the one thing that we know for sure that's not big data, okay, is what I call Paul Erdős. Okay? So I don't know how many of you know about this man. He's a great mathematician. Wrote many, many papers, and had a huge impact in the last century in research. And my advisor was a disciple of Paul Erdős and called him Uncle Paul. So I remember telling my advisor once that everything that Paul Erdős wrote, I could fit into a USB drive, and this blew Joel's mind because this was a century of research. So that's clearly not big data. It fits into it. Okay. So it's sort of interesting because at least when I started thinking about it, we used to talk about massive data, and there was a moment where we switched to big data, and we're still trying to sort of define the boundaries of things. Okay. But anyway, this is a background for us to get started with. The idea of streaming algorithms. Okay. So I'm going to just tell you one result, the Countman sketch a little bit, study some applications, and talk more about what systems and how do they fit in. Okay. So I'm going to just start with the Countman sketch part. By the way, I think about sometimes jokes which are of theoretical computer science interest. Okay. Yeah. So I think one of my favorites. I have quite a few of them. Now, how many theoretical computer scientist does it take to change a light bulb? Yeah, you can think of an answer for that. How do you take a picture of theoretical computer scientists? You ask them to say big O. I was thinking about log. What does a drowning theoretical computer scientist ask for? Log. It doesn't quite work well. So anyway, it's a whole class of jokes, which I have a lot of them. There are not many economists here, so I can tell jokes at the expense of economists. So there's a question of how many economists does it take to change a light bulb? Okay. And the answer is that none, because if the light bulb had to be changed, the market would have figured out a way to change it. So I want to talk about streaming algorithms, and I'm going to just give you talk with one result before I tell you how we came to think about this problem. Because in algorithms research, what we do is we solve a whole bunch of problems using the best because we like to solve problems. But at some point, we like to look back and see what's the simplest problem that I want to solve, and how do I use that to build up sort of a structure of problems, either through reductions or through sort of interesting ways of using them. And that's the way we build sort of the structure, sort of algorithmic knowledge. Right? You don't want to solve each problem separately using a whole bunch of technique, and you want to solve that, but at some point you want a general theory to come about. So the way I think about streaming algorithms now is that I think of this problem where there is a very large array. It's a virtual array. Since you cannot declare it, you're not going to use as much space as the whole array. And you're going to see updates into the array. So there'll be some increments and some decrements. Those are the updates. And for now, we're going to assume that the array is well behaved in the sense there are no negative items every time. Everything starts out with being 0, and things get decremented only if something got incremented, if that place got incremented before. Right? Okay. So you're sort of tracking all these transactions of increments and decrements, and once in a while you get asked queries about what is the ith location. Okay? What is fi? Okay? And of course, a trivial way to solve this problem is to declare a large array of size n, some sort of hash array, and then do all the transactions, and then anytime there's a query fi, you can look up the query easily. Okay? But we won't be able to do this because we're going to assume that we don't have space to declare the whole array. Okay? So we're going to use very little space, in particular something like log n space. Okay? The question is, how do we do this? Okay? There are many ways to do this. I'm just going to give you one solution. So the idea here is that many of you have seen this before. We're going to have, instead of storing one large virtual array, we're going to store a bunch of counters, a small number of counters. Okay? It is a two-dimensional array. Each row corresponds to a hash function, and what each hash function does is it takes its items 1 through n and maps it into a small range. That's the number of buckets, number of counters you see in each row. Okay? And you're going to use different independent hash functions for the number of rows. Okay? The two parameters you're going to pay attention to is that this method we're going to come up with is going to be approximate. It's going to be epsilon approximate, so epsilon is a parameter. And that's going to determine how many buckets we have. Okay? And the method we come up with is also going to be probabilistic, which means it will fail with some probability. And that's going to be the delta, which will determine how many hash functions we use. Okay? We use log 1 over delta hash functions. So number of hash functions is a function of failure of success of your estimation. And number of buckets or counters you use each row is related to the approximation that you're going to get. Okay? So what you do then is a very simple operation. Every time some operation happens on the virtual array, say some item I gets incremented, we hash I using the first hash function. It will drop into some bucket in the first row, and we will do the increment of the counter in that bucket. And we do that for each of the hash functions. Okay? So for each increment and each decrement, we compute the hash value of that item I according to each of the hash functions and perform the operation in the counter there. Okay? So update time is log 1 over delta because that's the number of hash functions we use. And anytime there's a query for what is fi, we have to find what fi is. Then we know that I mapped into, we can go and calculate for each hash function where the bucket it falls into, and that bucket corresponds to some counter. We're going to just return the minimum value of the counter. Okay? So those are the positions in the picture where I hashes onto, and we look. And anytime there's an operation of increment or decrement, we do that in the counter in those positions. Anytime there's a query for I, we return the minimum value of those counters. So that's an operation, and the claim we can make is that we're going to return an answer. So a priori, you can just look at the fact that f of f1 through n is a very large array. Think of millions, hundreds of millions, large size array. But n does not appear in this table as a parameter. So it's a small, it's only epsilon and delta. Right? So it's a very small array. Typically, we're going to think about 1,000 bytes or so. So clearly, you cannot be accurate on any large n. Okay? You can make n as large as you want, and you're going to be inaccurate. So you're going to have an approximate answer. You're not going to have an exact answer. And what we can claim about the estimate f tilde I is that it'll always be at least the correct value. Okay? You're going to always return an overestimate. Then how bad is the overestimate? It's going to be with some good probability or high probability. The estimate is going to be at most the correct value fi plus something that depends on the sum of all the values of fi. Okay? Now, this is not a very good estimate, right? Because if you're trying to estimate fi and f of I is 1, then your estimate is going to depend on sum of all other fi's, and there could be a large item like a million items sitting out there, and that's going to affect your accuracy of estimating fi. So if you're trying to use this to estimate fi where fi is small, it's not going to be a very good estimate. But if you're trying to estimate something which is large, then this will be a pretty reasonable estimate. Right? If f of I is like 1 in 100 of the total volume, then you can set epsilon to be like 1 in 200, 1 in 300, and you can get a pretty good estimate. Okay? So that's the way you want to use this in general. So of course, we found out the space is very small, 1 over epsilon log 1 over delta. Time to update is very small, like log 1 over delta. And those are the nice things. It's a very small data structure, but it gives you accuracy only for very large items. Okay? And since I mentioned Paul Erdős and I mentioned my advisor Joel Spencer, I always mention one of the quotes of Joel Spencer. He says that every talk should have a proof. Okay? And I'm going to have a proof. And then Ron Graham reminded me that every talk should have a proof and a joke. And then he pointed out to me that they should not be the same things. So here is a proof. We want to claim that the probability, it is very easy to see that the estimate that you return will be an overestimate because you're going to to estimate I, you're going to places where I hashed onto and return the minimum value of the counter. But whatever I was, whatever fi was, that incremented all of the counters where you visit. So you are taking all those effects into account. The only thing that you could be doing is that other items hashed onto the same bucket, so you could be overcounting. So f tilde I is at least fi, that's clear. The question is, how bad is the overestimate? And the way to look at the second term is, so the approximation is at most the correct value fi plus epsilon times the sum of all the other values. So the way to look at it is that if you look at a single row of a hash function, you know where the ith location hashed onto, and you're saying, well, I know all the transactions that happened to I here in the counter, but then a bunch of other items hashed onto this location, how bad could they be? Okay. Well, in the expected case, the contribution of other items to this bucket where I hashed onto would be the total sum of fi divided by the number of buckets. Because we're hashing them uniformly, just take the total sum and divide it by the number of buckets. That'll be the amount of volume that other items contribute to this bucket. Okay? So you're looking at where I hashed onto, and you're saying, you know what? All the updates to I got it in this counter, but other items also landed here, and they contribute to this sum as well. So how bad they can be, right? Well, the total sum divided by the number of buckets is the contribution. Right? So that's the expected value. So if you look at xij, which is a contribution of fj to a bucket where I hashed onto, that'll be sum of all of those things divided by the number of buckets. The number of buckets is E over epsilon. So 1 over epsilon is a number of buckets. So that expected term there is a total volume divided by number of buckets. And then you have a simple calculation that says, what's the probability that your estimate is worse than what you claimed? It's worse than what you claimed if this fi plus the contribution of others to this bucket is greater than the estimate. But if you just rearrange it, you'll notice that this reduces to saying, what's the contribution of others? the probability the contribution of others exceeds E times the expected value of the contribution. That will be 1 over E as a constant, using a Markov inequality. And then you repeat it for a bunch of hash functions, so that decreases the probability of this even further. Okay, that's the argument. So you might as well just understand the argument in terms of a single hash function. That we look at the ith location, where ith location hash down. Look at contribution of everybody else. It's the total sum divided by number of buckets. What's the probability that you exceed that? If you do the little algebra, you're looking at what's the probability the contribution exceeds a constant times the expected contribution. That's at most 1 over the constant. And then we repeat this a bunch of times to decrease the probability. Okay. That's a simple argument. Okay. I'm not going to go through this part of the proof. This part of the proof says that there's a very simple argument using communication complexity that shows that we cannot really do better than 1 over epsilon. Okay. The number of, here, the total amount of bits we stored here is 1 over epsilon log 1 over delta. The 1 over epsilon factor is something that we cannot really avoid. Okay. I'm not going to go through it because it's a very simple argument, and I have a feeling that in the talks in the future, some of it might come up. David may talk more about this. Okay. Or much harder proofs than the one on the slide. Okay. So here are some observations I want to point out. Right? Every time people see this, they say that this is like random projections, or Johnson-Linden-Strauss, or this is like Bloom filters. It is like Bloom filters, it is like Johnson-Linden-Strauss, it is dimensional reduction. If you go to data mining community, they'll say this is dimensional reduction. Statisticians say we reduce dimensions, and I believe it's all of them, but it's in precise detail that you see the differences. If you do most of the known dimensional reduction techniques, you use at least 1 over epsilon squared space, or you reduce it to 1 over epsilon squared dimensions. And that's not what we're doing because we're using 1 over epsilon space. And this is a key difference in the application. In a few minutes, I'll come to the systems we built based on this. And in those systems, 1 over epsilon squared space is something that we couldn't live with. We needed to do something better than 1 over epsilon squared. And basically, the observation here is that those dimensional reduction techniques do other things like preserving norms. Well, we don't need that for our applications. Point queries are sufficient for our applications, and that's all we need to work with. Okay? And again, this looks like hashing. Sure, you have to be very careful on what kind of hashing we use to minimize the number of bits. It's a technical argument. The other thing I hear when I talk about this to statisticians is that, well, it's an approximation. You can do it by sampling. Okay, this is a very difficult argument, very difficult viewpoint to argue against because sampling at some point is a linear projection, can be written as a linear projection, and then is really sampling or not is a hard question to argue against. But I have an example in my mind, a sort of a scenario that tells me why what we're doing is interesting, right? So imagine a world where you have about 1 million items, and somebody inserts 1 million items, and so Fi is +1 for 1 million items, and you had to keep a data structure of 1,000 bytes to track what happens in this 1 million items. Obviously, you cannot keep track of all the 1 million items with 1,000 bytes, right? And then sometime later, somebody comes and removes all but 4 of the items. Okay? Now your data structure has 1,000 bytes to track the 4 items. Okay? Now if you imagine any sampling procedure of 1,000 bytes of information here, the sampling procedure is not going to hit the 4 items that are going to be left behind, right? Because no, you're not clairvoyant about what are the 4 items that are going to be left behind, and any amount of information you keep about 1 million items, you will miss information theoretically, some of the items, and the adversary could just make sure that they keep those items behind. So a sampling method will have a very difficult time when you start removing the items. The only way you can keep a sample accurate is to go back and resample, but that you cannot do when you're not keeping track of them. Okay? On the other hand, if you use something like the count min sketch, then it has this linearity property that so if you insert 1 million items and remove all but 4 items, what you have is a count min sketch of the 4 items that are left behind. And you'll be actually accurately able to accurately retrieve the identity of the 4 items that you're left behind. Without any when you maintain a summary, you don't know which items will be left behind, but you can still retrieve them. Okay? So that's a kind of thing that tells me that the results that we get will be difficult to reproduce with sampling unless you do some very complicated resampling and going back to the database. So that's the power of this linearity. So what can you do with the count min sketch? Well, you can say, well, I have this data structure. Why don't I ask what is F1, what is F2, what is F3? You can ask each one of the queries at times, and you should be able to get an estimate for each one of them. Right? Many of them will give you wrong estimates because they're all small items. But the really good big items, I'll get a really good estimate. Okay? And those are what we call heavy hitters. And you can write down in terms of epsilon what heavy hitter means and see that you will get the very large items just by asking one question one after another. Okay? And that's an interesting question of interest. You're going to do a little bit extra space and time because you need to make sure that your accuracy of estimation is good for all the inquiries. So you're going to use a little bit extra space and time, but you can do this. Okay? I'm going to take one other quick step, which is if you don't want to spend time asking queries, what is F1, what is F2 up to Fn, n is a very large number, there's a quick way to make sure that you don't even have to ask all the n questions. Okay? You can do something called simple group testing to make sure that you only ask log n questions that will get you identity of these heavy items. Okay? And the rough way to think about it is that if you take n items and throw them into this k-squared or some buckets, then any item which you, if you only care about the k items, the k largest items, they'll almost always be separated. No two of them will land in the same bucket. And if that's the property, then in a given bucket, the items that land there which are large is going to be majority. They're going to be much bigger than everybody else. And it's not going to be large, but they're going to be larger than half of the other items that volume of the items land there. If that's the case, then you can do a simple log n type thing to find out. Things like, is the leading bit 1 or 0? Is the second bit 1 or 0? You can just binary search on the bit space and figure out what the item is that landed there. Okay? So just throwing into buckets will separate out the heavy guys, and then in each one of them you can do a slightly simple estimation procedure. Okay? So it's again the same kind of technique that you can use, right? So this gives you a version of what is called compressed sensing. If you heard about this, there's a lot of effort around compressed sensing. And this gives you one of the versions of compressed sensing results. And there's a nice website that compares this method with other more non-trivial methods for doing compressed sensing. Okay. This moment, I think I want to tell you one thing about. I don't know how many of you know Michael Rabin. Okay, an amazing researcher. Okay. I knew of Michael Rabin's work on randomized algorithms, and I know of him for a long time, but he spent 6 months visiting me when I was at Google, and we got to work together. It was amazing. Late 70s, 80s, whatever, old man, all kind of thing, but incredibly sharp. Every day come to work and said, what puzzles do you have for me today? and remarkable brain power. And if you know about him, then the one question that you may want to think about a puzzle is that he got a Turing Award, and you need to figure out what did he get Turing Award for. Okay? The idea is that since I know so much about his work, and most of his work is randomized algorithms, many people would guess that he got a Turing Award for randomized algorithms. But that's not what he got Turing Award for. He could have got one for that. But he got Turing Award for coming up with the notion of non-determinism, which is even deeper. So the question of P versus NP wouldn't make any sense without the notion of non-determinism, and that came up in his thesis. So remarkable achievement. So anyway, he came up with his ideas of randomized algorithms, and this is a randomized algorithm, and it's very simple. It's Matt said, so it's very, very simple. You can look at it, and pretty much you can write a code. In fact, the paper's written like it's a code. And so Michael Rabin also came up with lots of very nice simple algorithms, a simple algorithm for primality testing, for example. And once apparently he was giving a talk to the International Congress of Mathematicians, and I'm sure there are a lot of mathematicians in the audience, and you know what it is to talk to International Congress of Mathematicians. Okay, they expect to see incredibly deep results. And Michael Rabin gets up there and describes a simple algorithm for primality testing, and someone in the audience puts up his hand and says, but this is so simple. And Michael says, thank you. I love the story. So in some sense, I keep that as an inspiration for me, because eventually after you understood some things, you hope that you get really simple algorithms for some problem. And I think the Countman sketch is a really simple algorithm for a very simple problem on which you can do a lot of new stuff. Certainly when I heard compressed sensing for the first time in 2004, I was very lucky because people like Ingrid Dapschi and Ron DeVore explained compressed sensing to me, because it was a little bit hard to read the original papers of compressed sensing. And pretty much as soon as I heard them, I could reproduce the results using Countman sketch. Not the identical bounds is the best known for Countman sketch, but you could make a lot of progress using these methods. And that tells me that Countman sketch may not give you the best results in each of the problems, but it helps you get started. And then you can do more. Okay? And that's the way I think about it. I'm being a little bit on the high level. I know there are people in the audience who know the difference between L1 and L2 versions of these things and so on, but this is still a high-level message that has worked well for me. So we talked about heavy hitters, compressed sensing. You can use it for inner products, quantiles. There are ways to improve least square regression. You're going to hear some of the others, much deeper results about these problems, low rank approximation, and so on. I had this on the list here because some of this you're going to hear about later. Okay. And what has been interesting, this talk was about 10 years later. So I sort of went back and did a little bit of homework on what's happened with Counterpoint Sketch in the last few years. And because it is very simple and sort of there's a code for it on the web, bunch of versions of code lying around now, a lot of people use it. So I found uses for it in machine learning, something about hash kernels, and then there's natural language processing. The wonderful work of Michael Mitzelmarker on password checking, that a lot of fun, apparently. Okay, and I worked on using it for secure privacy. We set up a wiki site. There are tens, if not hundreds, of places where people have found ways to use this. And for me, a more interesting thing is that there are people actually writing code for this. Now, I was very excited to get an email from Joe Hellestein the other day saying, I'm on sabbatical, I'm working somewhere, and I thought, I'm writing a code for Counterpoint Sketch, can you tell me how this... Awesome, right? So people are writing code, and it's there on the web, you can use it. Some of their companies are doing it in hardware. I think that's pretty exciting too. And FPGA implementations, cube implementations, and GPU implementations. And so it seems like it's a very simple thing that has some use for it, so people find different ways to use it, and it's fun. Okay. So the reason I wanted to have this wiki site up there is that we talked about how it is hard for companies to interact with academia and academia to interact with companies. So the problem goes both ways, right? It's completely mutual. So I'm always reminded of this when I run into people in conference and they say, you know what, I haven't seen you in so long. And I'm like, I haven't seen you either. It's mutual, right? Something like this, right? Companies have difficult time engaging academic people, and academic people have very difficult time engaging companies, because there isn't a common language, and you guys are working out on examples of common language, right? So what I found is that if people can contribute to wiki sites, there are people who write code and they put it up there. They have links to them, and people are able to use it. But we don't often know what are the use cases. We don't know how people use them. We have to search research papers to find out how they use them. Well, even yesterday over dinner, I found that people are using them, which is a lot of fun to hear about, but they're not on the website. So it'll be nice to have some wiki way to interact with for both ways, right? Academic people will also like to hear about how these things get improved and modified, right? I mean, there's no academic research that directly gets applied. They always have to be improved, modified, and fitted in, and it'll be nice to hear about that as well. So let me just switch to how is it used in systems, and here is the place where you'll hear me speak much more passionately. Because I got thinking about the streaming problems in late 1990s and wrote a bunch of papers on using streaming techniques for wavelets, histograms, and complicated algorithms. And I wasn't really inspired by them. I was solving them because they're good theory problems. And then I got interested in building this IP traffic analysis system for AT&T. At that time, I was at AT&T. And there are a bunch of systems you could build. You could build a system that will just samples IP traffic data and then put it on a database and analyze SQL, write SQL queries. You could try to throw many missions at it, as Rob mentioned, right? So there are a bunch of different ways to approach these problems. And I was lucky enough to be with a group of people. We tried to attack the problem at a very very basic level. We decided that we're going to do interface cards, pull out the traffic. We're going to put a ring buffer so that of a few gigs so that it'll get filled up in a few seconds to a few minutes. And then we're going to write code on top of it to analyze packets. Okay? So what we were doing was, a good example to keep in mind is that you had to write a report that said for each source IP address of a packet, look at all the destination IP addresses and write some statistics on it, such as how many distinct IP addresses are there, which are the IP addresses which get most traffic, which are the IP addresses that get smallest number of TCP connections, and so on. So this is a very nice question to keep in mind because number of source IP addresses is a very large number of IP addresses. And for every destination, if you try, for each one of them, if you had to keep statistics about all the destination and store it, that's a large amount of data to store. Okay? I'll come to this in a little bit more in detail in the next slide, but the architecture that we worked out was something that I still enjoy thinking about. So we had little compiled C code which is low-level aggregators. They will pull out the packet headers as they come into the buffer and do some very simple aggregation, like hashing, sampling, like count, mean, sketch kind of things. And then they start doing it for every one of the source IP addresses. Obviously, they're going to run out of space at some point because the number of source IP addresses is going to keep increasing. As soon as they hit the space bottleneck, they flush it and send whatever they computed so far to higher level. And then they keep going on doing the same thing. Now, if you think about each source IP address, it gets a count, mean, sketch. It gets flushed up. And then it gets more packets sent from the source IP address. So a new count, mean, sketch gets built. But they use the same hash function. So the second time it gets flushed, what you have is a count, mean, sketch for 2 portions of the data. And if you add them up, you get a count, mean, sketch for the entire data. Okay. So the system design automatically sort of makes use of the fact that the sketch is linear. Okay. And the high-level aggregator, therefore, doesn't have to do all the work. It only adds up sketches, subtracts sketches, looks at differences, and does this kind of sketch arithmetic that you guys have developed so much. You're doing all set queries. You're doing set expression kind of arithmetic. They were doing very simple things like additions and subtractions. Okay. And this was the architecture. And this is now, it was at the time used to do a bunch of backbone analysis. And at this moment, it's operationally involved in, without going into all the details, it's operationally used by AT&T. Okay. So I have a reference just in case you want to check it out. This is only one of the example of queries. Usually, when you're running a IP network, you have 50s, hundreds, or thousands of such queries running in the network. Each one of them has a sketch. Each one of them flushes it, and the architecture is beautiful, so that everything sort of adds up, and you keep keeping track of statistics. Okay? So that's the basic idea. Okay? So the one thing I always keep in mind, I learned this from a previous company, was that someone there told me that an idea doesn't work unless you do. Okay? So this was our original idea, but behind it, there's a huge amount of sweat. Okay? We had to build a parallel system. They had to have a heartbeat going in so that we can actually execute without locking. We have load shedding. Yeah. I mean, then there's an enormous amount of system that you had to build. Okay? And so what do we learn from this? And I think here I can depart a little bit. Okay? We do algorithms research in a bunch of different ways, okay? And typically we tend to wear all these hats at the same time, right? Sometimes you do algorithms research and solve a problem because it's theoretically interesting, okay? So many of you looked at quantiles. A median is one example of a quantile, and it's a very interesting quantile. And people have looked at median finding algorithms for a long time. We're still trying to figure out what's the smallest number of comparisons needed to find the median, okay? And it was only a few years ago that I figured out that while there's 30 or 40 years of history on finding median of n items in linear number of comparisons, if you looked at the same question for strings and you looked at all the suffixes and tried to find median, we didn't have a linear time algorithm. So something that I worked on. Okay? So median tends to be a very interesting problem for which we do theory. Okay? And sometimes we do what is called applied research, right? And here I'm going to be a little bit more refined. Applied research is when, in the way I define it, is you get a problem, you solve a problem, and then you say, you know what, this could be useful to you guys. Okay? Here I have a nice Bloom filter, maybe you'll find a way to use it. Here I have found a nice compression, maybe you can find a way to use it. Maybe you have to sort of remove the heavy here, maybe you want the extreme items and then focus on a small subset, but my method will be applicable there. Okay? So that's typically how I think of as applied research. Okay? Somewhere a little bit more closer to reality for me is what I call the field algorithms. So I sort of ran an NSF workshop on it. We're running a program in NSF on some of these things. The idea here is that it's like field science research, right? If you want to collect butterflies, you got to go out in the field and collect butterflies. Okay, so I know this for a fact because, I was saying, Matt, that on Sunday I had to take my 3-year-old daughter on a hike, and she wanted me to collect butterflies. And here is the whole process of collecting butterflies. I spent 15 minutes stalking the butterflies, looking at the bush, go and grab it, and I hold it and I show it to her. She looks at it, she takes it out, and then she looks at it and she lets it go. And then she says, "Next one, Daddy." Again. So there's something about doing field science. It's something similar with doing algorithms and algorithms research. If you're in the field with the practical people, then you know the right problems and you know why some of the constraints make sense and some don't make sense, and you design algorithms in that space. That's a very nice place for me to do algorithms research. Okay? And there are Not that many opportunities to do that for academic people. Working with companies is the right place to do that. Okay? So I'm not even talking about academic people writing a theoretical problems, which are absolutely they should do this. I'm not even talking about theoretical researchers doing work which has applications. I'm talking about academic researchers sitting together with people in the industry who have the problems to be able to design algorithms in that context. And of course, later they can abstract up and write theorems about it, theory about it, but that'll be what I'll consider field algorithms research. And that'll be very desirable. And for me, this was an example, this Gigascope application I mentioned is an example of that because I wanted to just make sure I explain the field aspect of this carefully. If someone came and told me that design a problem, like the way I described the problem so far, I said solve this problem, but use small space, use logarithm space. Right? If you're in the field, you'll ask, why would I use small space? Okay. If my problem can be solved in half an hour by using large amount of space, maybe I'll do that way. Right? You're always trying, in practice, you're trying to solve the quickest way to solve the problem with which we can deal with it. Right? As a theoretical computer scientist, if someone told me use a log in space and solve the problem, I'm happy to accept as a constraint because it's an interesting technical problem. I like to solve the puzzle. I'm happy with it. Right? Someone had to make an argument to me that small space was important. Okay? And that argument cannot be that, look, space is expensive. Because the sufficient number of people will tell you that space is not expensive because I can buy a terabyte of disk very easily. So when is space expensive? This was a question that I was grappling with into 1998. And what I figured out was that in the IP traffic analysis world, space was expensive because the space had to be updated at the rate at which packets were going through the network. That's nanospeed update. Those memory items are very expensive. Then it makes sense in the router to do things with a small amount of space. Right? So you had to go to that level of detail for me to be even convinced that this was something worth doing. That someone had to make this argument for me. Right? And the second thing is that, say memory is expensive. Say there's a large stream of data going by, but you only care about something like ages of people. There are 100 possible ages, 150 possible ages. I can store the entire array of 100 and do all the computation I want. So that's not interesting by itself. If the memory can be expensive, the stream can be very fast, but the universe of the items I'm dealing with is so small that I can actually index everything. That's not an interesting problem, right? What was nice here was that in the IP address world, the space of IP address is so large that there is a space problem. So you had to think about that. Then I looked around at what we had at the time, and we used sketches which are all 1 over epsilon squared kind of space sketches. And my first attempt was to try to use them in the systems, and then I realized that in our application, we needed epsilon to be like 1 in 100 or 1 in 1,000. That was most reasonable, was that 1 in 1,000 was the epsilon. So 1 over epsilon of 1 in 1,000 means 1 over epsilon squared is like already a megabyte of data. Okay? We can't afford that for each source IP address. So that told me that 1 over epsilon, I had to figure out a way to get around the 1 over epsilon squared. And that's what the Countman sketch does, to get to 1 over epsilon. Okay? Now, I'm just telling you the kind of reasoning I needed to go through to convince myself that these were interesting problems for me to work on. Right? You could just work on them and saying, no, 1 over epsilon squared is a theoretical bound. Why not get the better theoretical bound? Okay? And that will work as well. In my case, it was useful for me to have these arguments for me to believe that the algorithm I'm working on had there was a particular system where it was important. Okay? Once you do this, now you can improve it in many number of ways. For example, I spent some time at Sprint where we could not even build the backbone at the time when Sprint was much bigger than the backbone rate at AT&T. So we couldn't even look at every packet. So we had to sort of skip over some packets. So you can think of it as sampling, but we were using the sketch to tell us how many packets to skip over. If you have a sketch and you have a norm of the sketch, that tells you how many more bytes you can skip before the norm is going to change, before any estimate is going to change. So you can skip that many packets. So we were using that to even go over those things, and then you can do things in a distributed way, and so on. Okay, so there's more you can do with this. Okay. That actually is. I was just waiting for a 5-minute. Oh my God! I can even tell you guys more stories. So by the way, throughout you saw some pictures in the background. Okay, I think they make the slides less readable. Okay. But I put the pictures in. I thought they were appropriate because they're all sculpture by a guy called Anish Kapoor. So I don't know if you know of him, but the Chicago Millennium Park, I think, is by Anish Kapoor, and he did something for Olympics. He's an incredible sculptor because he does extremely large scale sculpture, and the pieces of paintings that you saw are all from him. Background. Let me tell you a little bit about things I have not talked about so far. Okay, so I primarily just argued that when you're working on a real system, you need to be close to the system to know what problem you want to solve and what the constraints are. And I know this is obvious to most of you guys, but it's not. I need to remind myself of this many times, okay, because it's very easy to get caught up in a puzzle. It's exciting. You want to solve it. And for me, the excitement of working with Matt and Rob and others is because I feel like I know the advertising business very well. I know streaming maybe less so than I used to know before. But the kind of question they're asking, they're so close to these problems that I know that there will be new problems coming up if I just work with them. If I just talk to them, I know the new stuff will come up. And that's the excitement for me. If someone were to tell me that, come up with a sketch method that answers all conjunctive queries or all the subset queries, I'll say that's a nice generalization. But if someone tells me that this is the kind of thing that I need to write my reports or to explore it, then it becomes more real for me. Then I start thinking about where would I focus my attention. Okay, I will know what are the cases which will be sparse, what case I can focus on, and that's what makes it interesting. So there are a lot of things I didn't talk about here, which is, it's very exciting to talk about sketches. It's only a simple one-dimensional data structure, and we talked about this. There are a lot more things you can do with the sketch infrastructure. So, for example, if you're dealing with graphs, then you have sort of matrices, right? Vertex combination connections, and you can keep track of things for each person I and J contacts between the number of emails between them, the amount of bytes sent. You can think about this. And you might want to ask questions about this two-dimensional structure or even d-dimensional structure. And immediately you realize that, of course, you can solve many of these problems by looking at marginals and keeping counting sketch or some sketches in each of the rows and columns. But you might be able to do. There are cases where you may not even be able to do that. Okay, so I'm dealing with a company that gave me a problem in which they basically can't afford to store a sketch for each one of the row or each one of the column. So you had to be sublinear in the number of rows or sublinear in the number of columns as well. Okay. So you want to extend this sketch structures. There are problems, previous work on things like multigraph aggregates. I know David's worked on them, worked on some of these things. So a good way to extend some of this work is to say that what the sketches do is map the universe down to some small number of buckets and keep counters. Well, you could take an approach that says take a universe, map it to a small number of buckets, and within each bucket keep another sketch data structure. Okay. So you can take universe of 1 through n of source IP addresses, map it to a small number of buckets, and each one of the buckets keep a count min sketch or a distinct element sketch or nil sketch for all the destination items. So you can put the sketches together within sketches, and you can build interesting structures with them. They won't solve all the problems, okay, but they'll solve some of the problems. So you can do sketches for graph problems. There's been recent progress on some of these problems. Geometric problems. It was one of my earliest hopes that we'll be able to solve a lot of nice geometry problems using sketches, but there's been less success there than I imagined that we would have. Okay. There are other things like probabilistic streams, and they're nicely motivated in my mind because if you look at anything like an ad system, you have a lot of machine learning going on. So every query that comes in gets tagged by machine learning methods into something like spam or not, or interesting to a product or not, behavior of user or not. And all these are machine learning methods which are, honestly, they're probabilistic estimates. Okay? So what you have is a stream where each item has some sort of has a classification from some probability distribution. So now if you're given a sequence of such distributions, you might want to ask questions about the conjunction of all these distributions. They're very interesting questions you can ask. Okay? And I think those questions are interesting. They're not being looked at as much as one would imagine. Okay? And the other part that has not been developed is that we're still thinking in a very narrow way, like either use a streaming data structure to collect some data on which you can do a lot of database analysis, or put everything into multiple machines and do Rob mentioned this couple of the architecture points we explored. We're not exploring a lot more interesting architectural points we could, partly because we haven't found good applications, right? So ideally, you would think that there are all these sensors that are collecting this data from routers and they all send out data. You won't even optimize how much data they send out continually. Okay? So you don't want to sort of say every minute they send out some data. Every time they run out of space, they don't send out the data. These are all very simple methods. You could be much more smart about optimizing the bits and rate at which they send out the bits. Okay? So we have some results on what is called continual streaming. And even simplest problems become very interesting. So if they just said there are K sensors, each of them is seeing a bunch of items, and they're all talking to a center. And the center only wants to know how many items are there so far, seen by all of these items, all the sensors together. Okay? It's just a sum of all the items seen by number of items seen by sensors. If the center has to keep track of this information with some accuracy, what's the smallest number of bits that each of these sensors have to send in order for the center to be accurate? It turns out that in this particular example, the number of bits we can send will be independent of K, the number of sensors. In other words, each sensor, it's not the case that each sensor has to send even one bit of information. You can do an estimate even with a small subset of them are able to send the data. Okay? So that tells us that there's a lot of theory you can develop on optimizing the number of bits necessary to get something done in the center. I think there's a very interesting primitive like count mean sketch, but we don't have a system and an application on top of it to make it into bigger theory than it is right now. Okay? And it's always been something interesting to me. And finally, as some of you know, Berkeley has a Simons Center, which is a very large investment by Simons of Renaissance hedge fund to support theoretical computer science research, and they have a 10-year program. And the first year program begins this fall. Each semester there's going to be 2 programs with specific themes. And the first program, for first semester, we're going to have 2 programs, and one of them is on big data. Okay? So there's going to be one workshop on streaming and sublinear representation, and then there's going to be one workshop on sort of map reduce and distributed computing, one workshop on graph as a data structure, so all the graph problems, and another one on privacy. So that's all going to happen starting from August, September, I think. And there's a boot camp end of August to get all the people involved, and there are going to be a bunch of visitors, great theoretical group, wonderful set of research of people. If you think about anything about big data, you're going to find smart people there. Okay? So I hope you find a way to interact with them. And my contribution to the program is very small. I'm going to be there, and I want to learn from them. But I didn't make one non-trivial contribution. Okay? The logo was designed by me. Okay. Well, that's my non-trivial contribution to the program. I look forward to being there. Okay. And I look forward to the rest of the day. I hope to talk to you guys and find out more about things. I didn't go into details of many of the techniques. I'm sure most problems that you have in mind are much more complicated than once I talked about it. But it'll be an interesting intellectual exercise that no matter what complicated problem you give me, I'll try to solve it as in count mean sketch. Okay, that'll be an exercise. Except for the distinct element count, which I. Okay. Thank you, guys. Thank you.
Question?
No. Yes.
So a practical question is, for example, we are getting more and more data to the sketch table. So with the time progression, probably the quality of estimation will downward. So eventually, probably the sketch table will be exploded. So in practice, how do we solve this problem?
So this is a real problem. Okay.
Yeah.
So every solution I know segments based on time. So sort of keep sketch for one day, aggregate for a month, etc. But when you do that, you lose accuracy over time. It's a real problem, and I don't have any solution beyond the fact that in most cases I've dealt with this problem. The timescales of analysis are not. You don't store sketches for 2 years, 3 years, a year-long analysis. And you can usually find a reasonable segmentation and deal with accuracy issues. But I don't have a better answer than that. that's one solution that we explored in one of the examples. So, typically, we've been lucky because a lot of analysis tends to be recent analysis. So we keep sketch for real data for last 10 minutes, sketch for last 1 day, sketches for last week, or maybe a month, a quarter, maybe what marketing people. Beyond that, you are welcome to go to the database and rebuild it when you want to. Okay? At that time, at that level of accuracy, you can deal with it, but it still gets to be a problem if you take hundreds of router interfaces and ask some questions like, what happens if you look at union of all of these guys? You start losing accuracy, and that's a problem. So all of these things are somehow not graceful. You have an appropriate a priori bound epsilon that you use to descend data structure, and they're not graceful beyond that, and it's a problem. Right? So ideally, this is what I mean by we're exploring such small architectures, right? Ideally, you would like to have an architecture that keeps the data in the tape, then have something in the drive and something in the main memory, and knows when to rebuild as we go along. We don't have such an integrated system. We sort of use streaming system as a way to collect data and then a database on top of it. But I would love to, if we could build something more, if there were applications that really inspired us to build something in between, that would be nice. I don't know if any. But I understand the problem you're talking about.
I think it's kind of a boring question, but I'm sure you hear it all the time. But since F tilde is an overestimate, do you know, like, is there some of the corrections F tilde to make the error expected zero?
So you can do this. You can sort of subtract out various. You can make it not a one-sided error but a two-sided error by centering it the right way.
Yeah.
You can do that, and there are even people who looked at sort of things like assuming that your computer sketches. Maybe there's even better estimation procedure, not just the min and maxes, but something that solves some sort of a least error approximation kind of thing, maximum likelihood decoding, and people have looked at that kind of stuff. I'm not fully on top of that material, but people have looked at this. Thank you, guys.